Okay, so let's take a look at what's going to be on your Unit 4 exam. And putting this exam together this semester, it seems like there's fewer questions for this particular unit exam than you've had in other unit exams and than I give other semesters. So there you go. So the first thing I want you to know is the idea that all thunderstorm cells have 3 stages to their life cycle: cumulus, mature, and dissipating. And have a sense for cumulus stage is all updraft, mature is updraft and downdraft, and dissipating is just downdraft. So kind of have a sense for that. In the mature stage, of course, is where we have our heavy precipitation and the possibility of lightning and the audible thunder. And the mature stage is when you're going to have your hail and tornadoes, if the thunderstorm is going to give you that. Features of a thunderstorm cell. Notice the updraft is the kind of what's being fed. Here it's in red. The downdraft is in blue. Downdraft is associated with the kind of the wall of precipitation coming down. Overshooting top is kind of at the cauliflower crunchy looking thing that punches through the tropopause into the stratosphere. The gust front is associated with the downdraft. And then we have kind of associated with the gust front a shelf cloud. So know those things. Wind shear, and I think I misspelled this. I think it's SHEAR, but anyway, wind shear we said is basically as you go up in elevation, it's changing speed and or direction. And with regard to thunderstorms, wind shear will give you tilted. TS stands for thunderstorms instead of the majestic thunderstorms. So, and the tilted thunderstorms then allow for the updraft and downdraft to stay away from each other, and so it allows for it to last longer and be stronger. Then we talked about 2 types of weather systems where you have multiple thunderstorms cells at work. There's the squall line kind of over there at the right, and then there's the blobby one called mesoscale convective complexes, and they are blobby, so multiple thunderstorms. Remember, the mesoscale convective complexes are the ones that kind of occur maybe in the middle of the night. They're fed by that nocturnal low-level jet stream, warm, moist air. Let's see, did I have something for the next one? No, I kind of missed. Okay, so supercells, let's see. Let me add something to my thing here, if you don't mind. Supercell thunderstorms, they again have a cumulus. They start as cumulus, they go through mature and the dissipating stage. But supercells almost always bring severe weather. I'll put severe. And they last longer, and like I said, they bring severe weather. How's that? The next one, I don't generally test students over, can you describe how lightning occurs? So just in general, know that the terms leader, flash, stroke, and all are terms associated with the thing we collectively call lightning. Thunder basics, I went ahead and brought in a figure from your textbook at the top there. Or it's not a figure, it's the slide. So what do you need to know about thunder? Excuse me. Thunder is the sound associated with a lightning flash, and thunder occurs as basically when electrons kind of go back and forth between, if it's that 20% cloud to ground or 80% cloud to cloud lightning, when those electrons go kind of back and forth along that path, they heat the air very quickly, and actually the air then expands faster than the speed of sound, and that's what gives us our thunder. Let's see, what else? Oh, then the other thing, and I think it's coming up on the next item, there is you see the light right away. Light travels in air faster than sound travels in air. Actually, sound needs a medium to travel. So, but anyway, so you'll see the lightning before you hear the thunder, and that delay actually you can count. Let's go on to the next one. Remember, it's like a kind of a 5-second rule. There's 5 seconds. It takes 5 seconds to travel 1 mile, basically. So, for instance, if you heard, if there was a delay of 15 seconds, if you divide between when you saw it and when you heard it, if you divide 15 by 5, that means it's 3 miles away. I think that was one of your homework questions. And then there's a difference between the quality of the sound, the quality of the thunder. If you hear it clap, that means actually it's nice and crisp, and there wasn't a lot of space between you and it for it to kind of reverberate or bounce off. So it's pretty close. If you hear it kind of go whoa, 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 like an echo or a kind of what I call a rolling thunder, that means it's farther away. Heat lightning. Heat lightning, and I think in my lecture I usually say something about heat lightning is kind of sheet lightning. So heat lightning occurs on those warm summer nights, and heat lightning, as you may know, is like off in the distance. But the thing about heat lightning, if you're like me growing up, you know that you see it, and it's usually kind of up in the clouds, so it's that kind of sheet lightning. It's kind of the cloud-to-cloud sort of lightning. You see it in the far-off distance, but you can't hear it because the sound dissipates before it gets to you. So that's heat lightning. A wall cloud is a feature that oftentimes precedes the dropping of a tornado from a cumulonimbus cloud. So let's see, funnel cloud. By definition, a funnel cloud, or I think I might say funnel or funnel cloud, is a rotation that's dropping from a cumulonimbus cloud. It's basically a wannabe tornado, or a tornado that's kind of done its thing and is going back up into the cloud in a sense. So it doesn't touch the ground. The funnel cloud does not touch the ground. Tornado alley, and in my slides this semester I kind of looked at the old tornado alley versus the new tornado alley. The new one's a larger area. Basically, it's a place in North America where there's a kind of a hot spot of tornadic activity. The enhanced Fujita scale, or the EF scale, is the scale that we use to categorize tornadoes. And remember, the EF scale, or categorizing a tornado, can only be done after the fact. The darn things are so fast, it's not like they really get measuring equipment there. They gauge how fast the wind was based upon the damage that it did. EF1s are the tamest tornadoes, and I guess EF0s are the tamest tornadoes, and they are the most frequent. EF5 are relatively rare or infrequent, and they are most severe. And even though they're infrequent, the most deaths have been caused by these EF5s. So then on to Chapter 11, which is hurricanes. So the deadliest hurricane ever was Galveston, Texas in, I think it was the year 1900. Let's see. Different terms used for a tropical cyclone. So in Japan and that area, they call tropical cyclones typhoons. In Australia, they call them cyclones, and of course here in North America, we call tropical cyclones hurricanes. Features of a hurricane, so kind of know in general that in the center we have the eye, and of course at the eye, at the middle we have, the eye is pretty calm in the center of the eye, and we have a central low pressure. At the top we actually have a high pressure right above the low pressure of the eye, but and then outside the eye, we have the eye wall, and the eye wall is like where the winds are most intense, and actually they're kind of a circle of thunderstorm cells around the eye. And then we have the spiral rain bands that have tons of water that the storm system has picked up as it's cruised across the ocean. Okay. So 4 stages in the life of a hurricane, assuming that we're not going with the easterly waves, which is kind of a cool thing. But easterly waves are kind of where the thunderstorms kind of begin, as in we talked about the North Atlantic hurricanes actually start over off the coast of Africa. Anyway, the first stage is actually a tropical disturbance. followed by a tropical depression, followed by a tropical storm where it gets named, followed by a tropical cyclone. And we call tropical cyclones hurricanes. So those are the 4 stages in the life cycle of a hurricane. Easterly waves. Yeah, I brought in a figure from your textbook, so I kind of added the red there, showing you the kind of little cluster of thunderstorms that catch kind of a unstable air there off the west coast of Africa, and grab the easterly trade winds, part of the Hadley cell, come this way, and as they cross the Atlantic, they pick up warm, moist air and become stronger. Let's see, hurricanes. You've probably heard this before, that hurricanes can be upgraded and downgraded. Of course, they'll be upgraded as their energy increases, and they'll be downgraded as their energy decreases. Let's see. Okay, hurricane movement. I brought in a figure from your textbook. Remember, each one of those lines there actually is a different hurricane. So they actually kind of take this sort of kind of loop around the Bermuda High, that semi-permanent high that's between the Hadley and the Ferrell cell. So it seems like a lot of stuff that we've talked about earlier in the course is still kind of coming up. Of course, we call that recurving. Let's see what else. Oh, rules to naming your tropical storms. Remember, of the 4 stages of a hurricane, the third one, tropical storm, it goes ahead and gets a name. So I'll just kind of hit the highlights of this. I brought in an excerpt from the notes, but basically each ocean has its own set of names, which is kind of cool. Here, we in North America, we actually have a North Pacific and North Atlantic sets of names, the ocean basins, and so these actually we'll pick on just both basins. They alternate. They used to always be female. Now it's male female, which is nice. I know in the eastern basin, there are 5 letters that are hard to come up with names, and so they take these letters and they take them out. So names beginning with Q, U, X, Y, and Z are not included in the Eastern Pacific list. And so for both of them, actually, Eastern Pacific and the Western Pacific, if they run out of letters of the alphabet, what we'll do is go to the Greek alphabet, which is kind of bizarre. The year that Hurricane Katrina had its damage, we actually did, in that case, run out of letters of the alphabet and did that. Let's see, for both ocean basins that we're concerned with, actually there are 6 lists, and the lists, they cycle through the lists. So, yep. And then last but not least, if it was a particularly bad hurricane, that name will be removed from the list. So that name will be what we say retired. Let's see. Conditions favoring / required for hurricanes to form. The water needs to be sufficiently warm. Item number 2 there, you need to have enough spin. So the Coriolis force is what gives this large weather system spin, and so you run out of Coriolis force if you get too close to the equator. So even though it's the warmest water there, you have to be about 5 degrees on either side of the equator. And then the last one is you need to have unstable atmosphere. The next one, with regard to wind shear, and again I think this is SHEAR, wind shear and hurricanes. Wind shear actually encourages tornadoes, but too much wind shear at upper elevations will discourage a hurricane. Comparing hurricanes versus tornadoes. Now, hurricanes, actually, we do have reconnaissance airplanes that are measuring the wind speed, or measuring the wind speed is an indication of the strength of the hurricane or storm as it crosses the ocean basin. So unlike the tornadoes that are only measured or categorized after the fact. Let's see. So destructive forces of a hurricane. We have storm surge, and so remember what storm surge is, and I kind of have it in my review page here. Storm surge is a wall of water as the eye reaches landfall, and storm surge is strongest on the right side. Then we have tornadoes that are embedded in the eye. Anytime you see a thunderstorm, thunderstorms are kind of a multiple set of thunderstorms is what a hurricane is. So, yep, thunderstorms can bring tornadoes, so tornadoes are embedded in the hurricane. Flooding inland. Now, this actually I think might have been a homework question, but this idea of the spiral rain bands bringing all of that ocean water with it as it matures, that actually here in the Midwest, if we're going to get, if a weather system, kind of a petering out hurricane is going to go inland and get us here in the Midwest, it's going to be flooding from the spiral rain bands that gives us issues. And then the last one, who here in North America is tracking hurricanes, coordinating the efforts there, and getting out the warnings, the watches and the warnings? That would be the National Hurricane Center in Florida. On to the last chapter, weather forecasting. Okay, the first term, basically, we talked in this chapter about numerical weather forecasting and where we use computers, and it relies a lot on initial conditions. And actually, these initial conditions, I would imagine other kind of types of weather forecasting also rely on what is the atmosphere at the current time. And that's what we actually use to get our weather forecast. So initial conditions, we talked about ASOSs, those automated surface observing systems. Ocean buoys are great. Airplanes are great. Satellites are great for giving us initial conditions. Two types of weather satellites. We have geostationary and polar. And let's see. They differ by how they orbit the Earth. So the polar ones go every, I think, was it 100 minutes from South Pole, North Pole to South Pole, back to North Pole again. And they are relatively low, and there are advantages. Basically, they are great for looking at the polar regions. So I'm going to go ahead and kind of cross-reference on the exam. If you see polar, okay, really that is the POES, I think was what the textbook, this edition talks about them in terms of. The geostationary, I'll talk about those here in a minute, they are the GOES. So I hope you're going to be able to kind of make that leap on your unit exam. So the geostationary satellites is the one kind of shown down here, and it is cool because it the stationary part of geostationary means that basically it stays focused over one part of the Earth. Now these are limited to upper elevations, so these are farther up, which means they have a wider view because they're farther up. But the other thing is that they just hover over one location. So geostationary. All right. What else we got? Weather satellites. Actually, what they do is they change the wavelength, and in changing the wavelength, they can send back these three different scans. So we have visible images, we have infrared images that give us thermal information, and then we have a wavelength that is specific to water vapor. So those are the three types of images. Numerical weather forecasting. So I went ahead up here at the top and tried to kind of walk you through. So you're going to want to be able to kind of generally say what is numerical weather forecasting. I mentioned those initial conditions. So we take those initial conditions, and then when we put them into a forecast model, then the model is in a computer, so we use computers here. Then whatever that forecast comes out, we put those back in as initial conditions, and we kind of piggyback leapfrog our way into the future, kind of like that. So be able to kind of talk about that. All right. Climate forecast. So climatology or climatological forecast, those are the same thing. It's based on climate, and we'll be talking actually more about climates in the next unit. But we said climates clear back at the beginning of the semester was the condition of the atmosphere using like 30-year averages. So you kind of have a sense for what a climate is. So climatological forecasts are very vague. they're not too over the top extreme, very general. But they're useful in some parts of the world. The analogical forecast, the analogous means very similar. So what you do with the analogous forecast, analogous approach, is you look at today's conditions of the atmosphere and you compare what the conditions of the atmosphere are right now with some time in the past. And so whenever you find a matching day, then you see what the weather was tomorrow for that matching day, and that will be our weather tomorrow. Okay, so I hope that works for you. Nowcasting and trend forecasting are actually both related. Trend forecasting is the more general. Trend forecasting is to anticipate what the weather will do, kind of based upon our knowledge of, for instance, mid-latitude westerlies. Okay, so we can anticipate based upon kind of the way that system is moving and how that system is strengthened or petered out. We can apply that to know where it's going to go and what it's going to do. Nowcasting uses that sort of trend forecasting, but it's on a very short time frame. The next one, or the one kind of in between, persistence forecasting. If somebody is persistent, that means that they keep at it. So persistence forecasting says that the weather is going to persist. So basically, this says forecast is today's weather. So in other words, tomorrow's weather is what today's weather is. And actually that kind of works in some parts of the country. Or I should say, I don't know about the United States, but some parts of the world. Ensemble forecasting, remember that is where you actually make an ensemble or a set of weather forecasts with slightly different initial conditions. And the advantage here is that you can actually take a bird's eye view of that set of forecasts and then kind of see if you see a pattern, something that you want to put forth to the public as probably what the forecast, most likely forecast. The next one is kind of intuitive, that actually, if we look at our short-term forecasts, they are much more accurate than our long-term forecasts. Forecast bias, then, and I'm not sure this is in this edition of your textbook, but I think if somebody's biased, that means they're slanted. They're biased this way or biased that way. So a forecast bias means that actually you keep coming up like either high or you keep coming up with low for a particular forecast. So if that's the case, then you probably have something a little bit off with your model. So I hope that was helpful.